Hello everybody, I'm Nigel Forrester, formerly of Concurrent Technologies, now rebranded Concurrent to sort of mirror our sort of transformation into a more fast-moving, fast-paced type organisation. So what I'm going to talk to you today about is really a bit of a segue to some of the things that we discussed yesterday. So you might think, well, Intel processor cards, that's really, we've been around for a long time, we make a lot of these. I'm really focusing on around how we are delivering the best possible performance we can out of something that is in today's 3U, and I'm focusing on conduction cooled type format. And you might think, well, that's something you've been doing for 15 years, right? So there's nothing really exciting there, but actually the game has moved a long way in 15 years, and we're really using processors now that are very different and have different characteristics to the ones that we had before. So I'm trying to focus on what we can do, and there's a lot of, whilst I'm focusing on Intel processors, I point out there's a lot of parallels really with the other types of accelerators, so be it GPGPU or FPGA, very similar challenges. So if I look at the Intel sort of portfolio, swim lanes of the types of devices, I'm really only going to cover the first couple of devices here at the top. So the Xeon processors at the top here, this is sort of top end, comes from the sort of server or microserver down. And then what's shown here is now branded Intel Core Ultra processors is really the sort of the main line that's used in desktop sort of laptop type processors. I'm not going to concentrate on the Atom processors because if you can do something with a core processor, realistically, you can do it with an Atom. So it's not so challenging. So starting with the highest power type lane that we do at the moment, these are from what Intel calls the Xeon D type of product. They're designed for maximum CPU performance. There's a lot of good things about them. So the cores run at the same frequency, all cores are equal. And the type of processor that we're using at the moment, which looks like that thing in the sort of the top right here, which has got a nice metal can on, which we're very skeptical about at first because it's another thermal interface underneath the can, today we're running these things from the Intel Xeon D 1700 and 1800 product line, and they come from about 45 watts upwards. The top end processors in this line today are about 130 watts. So, we might say, well, what you really want to do is sort of use the highest powered processor, and that will give you the maximum performance. But in order to try and execute that and get the most out at the most cost-effective and sensible price point, unfortunately, there's this nasty thing called the law of physics. So it's really challenging within a 3U conduction-cooled environment to get out more than about 85 watts, something like that. Maybe a bit more, maybe a bit less, depends on the processor. Sometimes significantly less than that. So, just slapping on a 130 watt CPU with memory and everything else on there is not necessarily the best solution, as we will find out. So I've got a couple of examples using the sort of the current generation. So we've got a 10 core Xeon D 1746, which is what Intel calls their low core count. And in this particular processor, the base frequency for the processor is 2 gigahertz. You can enable turbo if you want. No, not many customers do that. We do allow them to do it, but we don't, as part of our qualification, enable turbo because it's non-deterministic. And running every single one of those 10 cores at that 2 gigahertz base frequency, we were able to qualify this at the ECC3 70°C card edge limit with no throttling. Fast forward to this year, we've done an update on that card using the latest generation Intel Silicon, which fortunately for us has a slightly lower power limit. It's exactly the same CPUs, same performance, but saves us 10 watts on the power, thanks Intel. And using a more exotic heat frame, which is probably more important, we actually managed to get this to a card edge temperature with no throttling at 85°C. Good. One small compromise is we had to reduce the frequency 5%, 1.9 gigahertz on the 10 cores. Still a good good process there. But what I'm getting to here is that before we actually started to work on these 10-core devices, we looked at whether we could actually do the same sort of thing with the next higher range of processor from the high core count range, which spans up to 20 cores, about 130 watts. And our simulations were that we could, but we'd have to run those 20 cores at less than half the frequency of the 10-core processor. So you actually get less performance, but you pay 2x the amount for the processor for the privilege, because Intel effectively prices things by the number of cores. So that didn't seem like a good solution to us. So for once, less is more. So sort of looking at things which probably a lot of people in this room know. What do we do before we actually produce these cards? We do sort of thermal simulations of the hotspots. You probably can't see the chart, but the bright red things at the top, and this guy here, a bright red, they're about 100 degrees C. That's not a problem, because these inductors and power supply components, they've got a TJ max of about 120 to 130 degrees C. Oops, back a bit. But this guy in the middle, the processor chip, which is a whole of this, and there's sort of two things on the die, this is where our problem comes in with these Xeon processors, because they only have a maximum temperature range of, if we're lucky, 100 degrees C, but sometimes less than that. So, 95 degrees C or less. And that's a real problem if you're trying to get these boards to run at an 85 degrees C, or even sometimes a 70 degrees C card edge in a conduction cooled environment. So we do lots of testing. We have all these fancy sort of test jigs that we run cards back to back, and you'll see why we do that in a minute. And actually, if I look, that was before the test started. When we're actually running the test in our thermal chamber, we cover everything up. It looks a bit crude, but we've got all these cables so that we can keep the power supplies out of the thermal chamber, and we can actually monitor what's going on the tests. And what we're really trying to do, to be realistic and to make sure that our products work as best as they possibly can, and that our customers will not find any issues when they're using them, is that in this block diagram here, what we're doing is we're actually executing code to exercise all of the interfaces and the devices on the card that are marked in green on this block diagram. And these are the high-speed interfaces, so PCIe, Ethernet, and things like that. Why do we do that? Well, that's because each time you run one of these interfaces or devices, it generates power, or it uses more power. And you might say, well, an M.2, PCIe Gen 3 by 4, maybe it's 2-3 watts. Yeah, it is, but that adds up. Every time you turn on a 10 gig Ethernet, that's another couple of watts. Turn on the 100 gig. Well, if you're actually using that 100 gig in anger, this is about 10 watts. So in order to qualify these cards, you have to run the interfaces at the stated frequency, and that's quite hard. But nevertheless, it's something you do, and it sort of works really well. And the sort of summary is that on the Xeon side, other than the fact that it's difficult to get to a max card temperature, they're actually pretty easy to qualify because all cores are the same, they're deterministic. We can actually deliver solutions which have zero throttling. So you can be absolutely sure that your application will run as you intended, and they're ideal for compute intensive tasks. So I've given the Xeon processors a nice tick. So then we'll come on to something a little bit more interesting, which is these Intel, what are currently branded Core Ultra processors. And for those of you who've been around a long time, Intel's marketing team have great fun in rebranding these things every couple of years. So they were Intel Core processors, they've been branded Intel Xeon E's, Xeon W's at various times, but they're fundamentally from the sort of the mainline processor. And you can see from the sort of image here, the look of the processor. They tend to be quite long and thin, which isn't terribly helpful. But what I have done here is I built on a presentation which some of our colleagues from Curtiss-Wright did last year about the hybrid nature of the processors here in core and threads. So very brief recap for those of you who weren't here last year. These processors have a hybrid architecture. They have both performance and efficient cores, completely different types of cores, and fundamentally they're there for different types of processing. somewhat analogous to the big little type of thing that ARM does, where you're using the big cores or Intel cores and performance cores, which are physically larger for the real heavyweight crunching number type work that you want to do. And these currently are capable of hyperthreading, although Intel is changing that as well. Whereas the efficient cores are really all about how do you get the most power efficient processing. So they're physically smaller, optimized to run background tasks. And to make life even more interesting, on the current generation of Intel processors, they've now introduced also low power efficient cores. Didn't put it on the slide. They're functionally equivalent to the efficient cores, it's exactly the same type of core, but they're on a separate power structure that Intel calls a low power island. So if you want the lowest power consumption possible, you can power just the low power island and just those super efficient, low power efficient cores, which does add a little bit of extra complexity. So from the perspective of this presentation, what I also wanted to make sure you're aware is that these run at different frequencies and they're actually different cores. So current generation, you might pick a device that has a performance core, the base frequency is about 2.4 gigahertz. The efficient core, the base frequency is 1.6, for example. They also support turbo frequencies, although again, we disable those by default. But with these types of processors, the difference between the turbo and the non-turbo frequency is very dramatic. So a performance core, a base frequency of 2.4 gigahertz, the turbo frequency might be 4.8 gigahertz. So very different. Right, so how does Intel, when you're using these sort of processors, how do they control what goes onto a performance and efficient core? They have this thing called a thread director, which is a small microcontroller. And it does this by analyzing and then feeding information back to the operating system. And it does this in a dynamic way. Again, not really what you want for your embedded system, because you don't want things to be moved between cores or have different type performance depending on what Intel believes that is what they think. And there's a nice little tool called Intel Thread Visualization Tool, which tells you what's running on which core. It even gives you a little diagram down here that says these two blue things are the performance cores and these things down below are the efficient cores, and it tells you, how much of each type of core, and depending on what applications you're running, it sort of scales up and scales down, and you can get all sorts of different metrics out of this if you really want to. As I said, sort of not really ideal for your embedded application. So what can you actually do about it? Well, obviously, Intel makes it quite tricky, because you can't disable that thread director, but you can circumvent it. So you can do things like turn off specific types of cores, or you could manually post your thread to a specific type of core, and that's the sort of thing that we do in an embedded application. To add another level of complexity, in these types of processors, they also have accelerators. So both GPGPU and now for the next generation of embedded computer processor, these neural processor units. And that's because the neural processor unit is because Microsoft insists to be Copilot Plus stated. You have to have a neural processing unit. And that's because they want to execute on device AI applications. So great presentation from the previous speaker about AI, but they want trying to do that at the bottom end of your actual device. And Intel's view of the world is that because they've got all these different types of accelerators that work better for some applications and not so well for others, with their OpenVINO tool, you can heterogeneously run an AI application, and it makes use of the best processing resource. If you're not doing AI, they also have another tool called One API, which does the same sort of thing, and you program that using a language called Data Parallel C++. So there's lots of information online if you want to have a look at that. It's quite interesting. Some of our customers do want to do that, some of them don't. So how do we, one more challenge I should say, and that is that every time they do a die shrink, what that really means is that the power density increases. So 15 years ago, we probably had 35 watt devices that were sort of this big. Now we have 35 watt devices that are this big, where they've concentrated the actual CPU cores into very small space. And that is really challenging from a thermal perspective of things like VPX conduction cooled. There are other challenges as well, because from our point of view, how do we classify a realistic load for our customers? You know, do we try running all these devices? How do we minimize throttling? You know, so we do exactly the same sort of thing that we do before with the Xeon processors, but it is more challenging. And I'm not sure that we yet have all of the information that we need to make that work for all of our customers. But what we try and do is to come up with a scenario that we think fits reasonably for most applications. And this is a recent card that we did the previous year, where we're running the CPU cores around about 1.6 gigahertz, whether they're performance or efficient cores. So the similar CPU speed, although different types of cores, with a relatively small amount of GPU. We do the same sort of testing, so I'm not going to go through that. We exercise all the interfaces. And at the end of the day, what we're really trying to do is to give our customers the most performance in a realistic way. However, what I would strongly recommend or advise is that every application is different. Try it if you can, ask for information, because this is only going to get more and more interesting as we go on. And one of the really good things about some of the things that we talked about yesterday is that that will help us solve some of these problems, because the challenges become somewhat easier in the new formats. And with that, I will wrap up. Any questions?